Welcome to this lecture. In the past few lectures, we have been extensively discussing about measure theoretic integration. We have seen many of the important properties involving certain limiting behaviors. Alright, so with that setup, it is now a good time to understand where this integration procedure stand with respect to our usual integration procedure, which we call as Riemann integration. So in this lecture, we are going to start exploring the connection between Riemann integration and measure theoretic integration. We move on to the slides for the discussion. So we are working with Riemann integration on the real line that we know about, and what we are going to consider as a special type of measure theoretic integration is the integration with respect to the Lebesgue measure lambda on the real line. Okay, so you are going to compare these two things. Now the second type, for ease of communication, shall be referred to as the Lebesgue integration. So any integration of a measurable function with respect to the Lebesgue measure will be referred as the Lebesgue integration. Alright. Now another important notational issue, just to clarify, is that in this lecture there will be two types of integrals appearing. One will be this Riemann integrations, the second one will be Lebesgue integrations. Now just to distinguish which integration is being interpreted in the Riemann sense and which integration is being interpreted in the Lebesgue sense, we want to clarify certain notations. So for Riemann integrations, what we will do, we will write it in the usual integration of a integrand with respect to dx, but in front we will write in brackets capital R to denote Riemann integration. The Lebesgue integrations will be denoted as integration with respect to the measure lambda. That's as per the usual notation that has been used so far in this course. And more explicitly, sometimes lambda dx may be explicitly written. Otherwise, it will be simply the integrand, that function d lambda. That integration symbol will refer to Lebesgue integrations. Alright, so now a few comments about Lebesgue integrations that requires justification. First, start with a measurable function on the real line, taking real numbers as their values, and you also fix some bounded interval AB, okay, closed AB. Now consider this integration of the function over this set closed AB. That is, as per definition, integration of f times the indicator of closed AB with respect to the Lebesgue measure. But now recall that Lebesgue measure associates mass 0 to singletons, and in particular here the boundary points A and B, those singleton sets will be associated 0 mass by the Lebesgue measure. Now by an earlier discussion on the Lebesgue measure, you can now claim that integration of f over this set closed AB will be the same as integration of the function over this open A to closed B, or closed A to open B, or open A to open B. Okay, so whichever type of intervals you prefer, as long as these sets differ only by sets of measure 0, the integrations will not change. Okay, so that was the discussion made in note 4 earlier. Alright, so again, just to be clear, if one of these integrations exist, so does the others, and the equality holds. So that is the meaning of this here. Okay, but this is for a function defined on the real line taking real numbers as their values. But now there is a related concept of restrictions of functions and measures. So what is this? So continue with that interval as above. Now what you can consider is that you can look at the Lebesgue measure restricted to an interval closed AB. Right, so this was discussed earlier in note 24 of week 5. Just to recall, there we had considered intervals of length 1 But in general, you can look at any such closed bounded interval AB and restrict the Lebesgue measure to it. So it does the same construction all over again. Okay. But here you might not get a probability measure, you will get a finite measure. Alright. So suppose you take any measurable G defined on the closed interval AB, taking real numbers as their values. Then for all such G, you can try to integrate the function G with respect to the Lebesgue measure restricted to AB. So now Lebesgue measure restricted to AB is a measure on this measurable space AB together with the Borel sigma field. And here the integration of G is over the actual domain which is closed AB. So here we are not looking at a subset of the domain. Here the domain is closed AB itself. So here you can consider this type of a integration, right? Now just to avoid any further confusions, we use this simplified notation that we will take it to be the Lebesgue measure itself on the closed interval AB. Okay. So just to stop writing this restriction symbol here, we will simply write d lambda here, but we will understand as long as G is given to be defined on this closed interval AB, this is the integration of G with respect to the restriction of the Lebesgue measure to this interval. So that will be the understanding, but here we are going to use this simplified notation. But with this as the motivation, let's look at a few properties that are left as exercise for your verification. So continue with the function f as described above. So here we are taking the function f to be defined on the real line and taking values within the real line, and you want it to be measurable. Now if you continue with that same interval, closed bounded interval AB, then you can show that restriction of this function to this interval will be measurable. Okay, so here you are putting the appropriate Borel sigma fields on both sides, on the range and the as well as the domain. Okay, so with respect to these appropriate sigma fields, these restriction functions becomes measurable. You can check this. But then once you have restricted this function, you can now consider the integration of the function, the restricted function, with respect to the restricted Lebesgue measure, and that integration will be over the actual domain here. Now the actual domain is closed AB, right? But you can identify or show that this value is nothing but integration of f with respect to the measure lambda on the set AB. So this is in the sense of integration of a real valued function defined on the real line. So that means on the right hand side it is taken as integration of f times the indicator of the closed bounded interval AB. Now this equality will hold if any one of the integrals exist. You can show the existence of the other and you can show the equality. Okay, so that is the idea. So this is why we are not focusing on restriction of lambda. We will in general write lambda itself. We are not going to carry around these restriction functions. It will be clear from the context which Lebesgue measure is getting used, but the understanding will be that the measure has to be on the appropriate domain spaces. Alright. Now here we start the discussion about the connection between Riemann integrations and the Lebesgue integrations. Remember, the Riemann integration was motivated as the area under the curve. Similarly, when we started the discussion about measure theoretic integration, we started by looking at area under the curve of indicator functions, and then both these integrations took over from there, from these basic definitions, and then we tried to extend these notions of integrations to the appropriate class of functions where the integrations can be defined. So this is true for both Riemann integration and integration with respect to the Lebesgue measure. Now both these integrals are trying to compute the area under the curve for any general function. In a general notion, there are certain differences. So before we go into the actual theoretical results, let's just do some preliminary comparisons by looking at various functions as examples and see if there are any differences. So start with f defined on the real line and taking values in the real line. Okay. So while talking about Riemann integrations on these closed bounded intervals, you would typically work with bounded functions. While you are talking about the Lebesgue integrations, you would need these functions to be measurable. So a priori, there is no direct connections between the hypotheses. So we will see the connection when we do the theoretical analysis. But start with f, which is an indicator function of an interval of the form closed 0 to closed 1. Okay, so this is the closed bounded interval 0, 1. More explicitly, this is the function that takes value 1 on this interval, otherwise it takes the value 0. So remember, this function has finitely many discontinuities. Discontinuities appear at this boundary points 0 and 1. So this will be Riemann integrable, and therefore you can also compute the Riemann integration of this function, that will be 1. Okay, this is just simply the integration of the constant function 1 over the interval 0 to 1. So that will give you the value 1. What happens to the Lebesgue measures situation? So if you want to integrate the function against the Lebesgue measure, observe that this is a genuine measurable function. It is just a indicator of this measurable set closed 0 to closed 1. Okay, so as per definition, this will be the Lebesgue integration. So we are writing L just to highlight this distinction. So here what is happening is that you are integrating this indicator function against the Lebesgue measure. So you get the length of the interval as the value of the integral. This is as per definition, and that is nothing but 1. So here you get that the Riemann integration and the Lebesgue integration match. Now you can try to check a different quantity. Now you can try to integrate the function over this interval 0, 1. So earlier this integration was over the whole real line, but now we are doing the integration only over this closed bounded interval 0, 1. And as per definition, this is the integration of f times the indicator of this set, and again if you do the computation, it again gives you the value 1. So for this specific function indicator of 0, 1, if you do the Riemann integration or the Lebesgue integration, do integrations over this interval 0, 1 or this interval 0, 1 here, all are matching in this specific situation. So let's now take a slightly more general example. So suppose you look at the set of rational numbers and look for all rational numbers contained inside the closed bounded interval 0, 1. So look at all such rational points there. So then define the function to be 1 on those points, otherwise you define it to be 0. So this is the indicator of the set of rationals contained within the closed bounded interval 0, 1. So that's this indicator function. Now observe that f is discontinuous on this closed bounded interval 0, 1, and you can show that this will not be Riemann integrable. Okay, you can take it as an exercise. But then this function is a genuine indicator of a measurable set, a Borel subset of R, and therefore you can consider its integration, and that's nothing but the length of this set. And then note that this set here, this is a subset of the rational numbers, and since rational numbers are countable, this subset also is countable, and Lebesgue measures assigns 0 mass to all countable sets. So therefore the area under the curve here, in the sense of Lebesgue integration, this is 0 here. Alright, so that's interesting. Now here f is non-negative, so you can talk about Lebesgue integrability here. Okay, so here the function is not Riemann integrable, but it is Lebesgue integrable. So this is an important example. Now we make the previous example slightly more complicated. So consider this specific set of rational numbers such that it has a form p by q, with q taking values between these natural numbers 1 to up to n, but p can vary from minus q to plus q, okay, including 0. So p by q, only p can take signs, q is a natural number. So you are looking at those type of rational numbers which can be written as p by q form with this range of p's and q. So here this range of q is dependent on this natural number n, and therefore you look at this set of rationals and denoted by q subscript n. Now it is easy to check that q subscript n is finite, because you are only allowing finitely many choices of q, and for each choice of q you are allowing finitely many choices of p. So you have that this rational numbers which are of the form p by q for this range of q's and p's, this set of rationals is finite. But then observe that as n increases, these qn's also increase, they get larger, and they will eventually cover the rational number set, meaning their complete union, countable union, is the rational number q itself. So therefore you can immediately claim that 0 1 intersection with qn, meaning this specific type of rational numbers within 0 1 will increase and increase to all rational numbers within closed 0 1. But then you can also look at the similar feature in terms of the indicators. As long as these sets increase to this set, you have the indicators, corresponding indicators increasing to this functions, which is also an indicator. Okay. Now here it's interesting that the functions fn for each fixed n are Riemann integrable and Lebesgue integrable. Fn's are Riemann integrable as well as Lebesgue integrable. But the limit function which happens here, this function f, indicator of rational numbers within 0 1, that indicator function, this limit function is Lebesgue integrable but not Riemann integrable. So limit of Riemann integrable functions need not be Riemann integrable. So this is a important comment about Riemann integrable functions. Okay. So with these observations at hand, we have already noted certain important distinctions between Lebesgue integrations and Riemann integrations. Okay. So now here is the concrete theorem which we want to focus on. So look at a bounded function defined on this closed boundary interval AB taking values in the real line. Now start by assuming that f is Riemann integrable. Then you can show that f is Lebesgue integrable and the Riemann integration, whatever the value, will match with the Lebesgue integration value. So again we are highlighting within bracket L here just to denote that this is Lebesgue integration. Okay. Of course the Lebesgue measure is appearing here, but just to clarify we are writing this bracket L to denote this Lebesgue integration. So what we are saying is that if you have Riemann integrability, then you get Lebesgue integrability and the values match. So therefore if you get a function for which you can compute the Riemann integration, then you do not need to separately compute the integration with respect to the Lebesgue measure. You can just take the value that appeared from the Riemann integration. Okay. So this is an important observation. And here is an important classification or characterization of Riemann integrable functions. If is Riemann integrable, then it happens if and only if the set of discontinuities, meaning the set of points where f is discontinuous, that set of points has Lebesgue measure 0. So this is the important identification of Riemann integrable functions. Okay. Now if it so happens in this case, if f is Riemann integrable, then you get this statement that f is continuous, Lebesgue measure almost everywhere. So by that I mean that outside some appropriate null set which contains this set of discontinuities, f is continuous. So here this is an important characterization of Riemann integrable functions. Okay. So this proof will be discussed later in the next lecture, but there are a couple of important comments here. In particular, let's focus on part 1. So in part 1 we are saying that f is Riemann integrable implies f is Lebesgue integrable. But remember, before even you talk about integrability, you have to justify that f is measurable. So this will require proper justification and this will be included in the proof. So that is included certain appropriate technical statements. So all these details will be discussed in the next lecture. But now we are going to focus on this interpretation of these results. So keeping this idea in hand that whenever you can compute the Riemann integration, you immediately get the value of the Lebesgue integration. So that is the main content of the previous theorem. So with that in mind, then what you can say is that the Lebesgue integration as written here is essentially some kind of an extension of the Riemann integration. Okay. So as long as Riemann integration exists, you get the same value for the Lebesgue integrations. But there are functions, remember, there are functions which are Lebesgue integrable but not Riemann integrable. So this is important. Okay. So just to identify that Lebesgue integration is essentially an extension of the Riemann integration, we will use this simplified notation for the Lebesgue integration. Now that Lebesgue integration over closed AB will be taken as integral from a to b fx dx. So we will suppress the symbol lambda, we will simply write this. So if you can compute it in terms of the Riemann integration, the same value will be given to the Lebesgue integration. But if you cannot compute it through Riemann integration, try it directly through the Lebesgue integration. Okay. Now it is important that we are using this symbol, but the justification is that this is a simplified symbol saying that Lebesgue integrations match with Riemann integrations provided the Riemann integrations exist. Okay. Alright, but remember there are Lebesgue integrable functions which are not Riemann integrable. So this is very important. Alright. So now what happens if you want to discuss Riemann integrations with improper limits, meaning infinite limits, possibly over the whole real line. Now here we are focusing on this type of integrations. Now if f is bounded and Riemann integrable in this situation, then you can possibly try to justify this set of equalities, that Riemann integration over minus infinity to plus infinity is essentially limit as n goes to infinity the Riemann integration from minus n to plus n of the function. But then on these closed bounded intervals you have identified that the Riemann integration and the Lebesgue integrations match. So you just replace the Riemann integration by the Lebesgue integration, write it with respect to the measure lambda. So this is integration from minus n to plus n, that integration. But then if you can justify the existence of this, then these functions pointwise approximate the function f over the whole real line. So f multiplied by the indicator of these intervals as n increases will approximate the function f pointwise. Okay. So as long as these limits exist, you can justify all these equalities, then Riemann integration and the Lebesgue integration will match over the whole real line now. Okay. But for that you have to justify all these limits and the value that appears in the limit. Okay. So you have to justify all those things. But this is the formal equalities that we can use. So therefore again, exactly as done for finite intervals, bounded intervals, you can also do the same for integrations over the whole real line for the Lebesgue integrations, that you write minus infinity to plus infinity fx dx as a shorthand notation just to identify that whenever Riemann integrations exist, it will match there. Okay. So this is just an extension of the usual Riemann integrations. But then there are also improper integrations where you deal with singularities of the function. So singularities may appear as an interior point of the domain or at the boundaries. Okay. Now here if you can identify the Riemann integration, then it will require certain technical justification, right? So there are appropriate ways of defining Riemann integrations. We are not going to recall this, but once you can define Riemann integration or your function is Riemann integrable, in this situation you can consider the connection with the Lebesgue integrations once more. What you can say is that the equalities will still continue to hold, but to avoid these technical details, we are going to assume this equality. We are not going to discuss in complete detail the actual equality or the proof. Okay. Alright. Now we finish the discussion with a pictorial comparison of the ways of Riemann integrations and Lebesgue integrations. And for simplicity, we are going to work with bounded and non-negative function f defined on such closed bounded interval ab and taking values in the real line. So assume that f is Riemann integrable. So here is where you can now compare the area under the curve in these two different ways. One is through Riemann integration, another is through Lebesgue integration. So let's try to look at in the Riemann integration setup. This what we do, we vertically split the domain side, right? So if your function graph is something like this, you look at this domain a to b, you split it vertically and try to fit in some appropriate rectangles which will approximate the area under the curve. Okay. So you vertically split the domain and try to compute the sum of these areas of these rectangles. So as long as your partitions on the domain side shrink, you get finer and finer approximations to the actual area under the curve. So that's what Riemann integration is all about. But what happens for the Lebesgue integrations? Remember, if you are dealing with this non-negative and bounded function, let's say you have justified integrability, then what you will do, you will approximate it through simple functions, and you will use the area under the curve for simple functions as a approximation for the area under the curve of the original function f, right? So the idea is this. So as soon as you are approximating this non-negative function f by simple functions from below, then what you are actually obtaining is a different type of splitting the area under the curve. Okay, so here you are looking at range of values for the functions. Within those specific range of values, these are now horizontal strips. So this will denote specific range of values, small range of values, and for these strips you are approximating it through the appropriate simple function, which takes some boundary value as the approximation of the function. Okay, so go back to that approximation by simple functions, try to look at the definition of the simple functions there, and you will immediately observe that the lower boundary value for the function is taken as the approximation simple functions value. Okay, so you are splitting the area under the curve in a horizontal sections now, horizontal strips, and now you are putting them together. So what do you do here? Observe that for this example here, the area here is the length which is given by the appropriate measure on the domain side multiplied by the function value, right? So that will be the area under the curve for that simple function, that contribution. Again, remember that there might be situations where there are two parts in the domain which take this same range of values. So for example, this dotted part here is two possibly disjoint parts where the same range of values are being taken. Again, the values for the function will be approximated by a lower end point here, and you just look at the total length, this part dotted and this part dotted, as given by the domain side measure. Okay, so that will give you an approximation for this area. Okay, that is the idea. Now Lebesgue measure or Lebesgue integrations, what they are doing, they are splitting the area under the curve in horizontal strips, and in Riemann integrations you are splitting it into vertical strips. So that's basically the pictorial comparison of Riemann integration and Lebesgue integration. But it so happens that all Riemann integrable functions are Lebesgue integrable, but the converse is not true. So what is happening is that in some sense splitting it through these horizontal strips is allowing you to integrate much more functions, much more bad functions which need not be integrable in the Riemann sense. Okay, so this is a very important clarification regarding the Lebesgue integration, and this discussion we will formalize in the next lecture when we prove the exact connection between this Riemann integration and the Lebesgue integration as stated here in theorem 5 discussed earlier. We will continue this discussion in the next lecture.